Good. All right, so we're ready to go. So it's rainy, so not great for observing, but on the upswing, we didn't get hit by a re-entering Soviet satellite. Yeah, it came down somewhere in the Indian Ocean. Yeah, good place for it. Last this I heard was the Indian Ocean, but a lot of uncertainty. Okay, so start off with the our traditional Indigenous land acknowledgement. RASC Halifax Centre respectfully acknowledges that we live and observe on the unceded territory of the Mi'kmaq people. So the RASC believes in and practices inclusivity and diversity. Halifax Centre welcomes all with an interest in astronomy without prejudice. So today's meeting, we'll continue on with a photo montage. Judy's got some of the universe guides for sale. No, none today. Oh, okay, we're sold out on those too. So calendars are gone and guides are gone. Our special presentation today is by Blair McDonald, who will tell us everything we wanted to know about black holes. We'll have a social break then. Then Paul Heath will give us food for the soul. There'll be news from the board following that, and a National Council update, and comment on outreach and what's up in May to end the meeting. No, montage. Bottom. There. Images that were captured by RASC Halifax members in April, the occasional clear night. Judy Black starts us off with this image of Messier 5, globular cluster found in serpents. We're not clicking. Did that work? Nope. Just hit the next one, Jerry. Right now. Oh. Oh, right. It's working now. And Michael Bochet took a shot of the moon on the 28th of April. A nice slim crescent with earthshine, and Messier 45, the Seven Sisters up in the corner. And a little bit later, another shot of the moon and Messier 45 with the earthshine much more visible. Again, taken from Michael's apartment through the window with a DSLR held up to an eyepiece. And Michael got this shot of sunspot group AR 4079. You can see it up here. And a an enlarged view. People were calling this the snout for obvious reasons. And it was an interesting sunspot. It was very large. It was about half the size of a Carrington sunspot, so it was a big sunspot, and it was surprisingly quiet. It unleashed a few C-class flares, but nothing of any significance. Dave Chapman took a shot of the waxing crescent moon, the gang of four nicely visible, and Mercurium. And they've also sketched the sun on the 30th of April. Again, there's that big sunspot, 4079. And Jason Dane, still taking pictures in Northern Lights. He got this in mid-April while he was in Sweden. Jeff Donaldson captured this many, many hours of integration shot of Messier 101 in Ursa Major. And Messier 106 in Canis Venatici. And some nice smaller galaxies. This one in particular stands out nicely with that dust band, very visible. Tim Doucette trying out his C-Star S30 took this shot of Messier 51. And with a DSLR, I believe, got this shot of the Milky Way overhead. And finally, this is Tim's shot of the crescent moon on the 29th of April. Lisa Ann Fanning got this shot of Venus and the waning crescent moon, and although it didn't show up in the Facebook image on here, I think this is Saturn. So she got the smiley face. Now we're dead again. Yeah. This is another one from Lisa Ann, Jupiter and the crescent moon on the 30th of April. This is my shot of a large sunspot. This was AR 4048 on the 2nd of April. And the waxing gibbous moon on the 11th. Draco triplet, 3 galaxies. One, I believe, is elliptical, and these 2 are spirals. One edge on and one face on. And a solar prominence, very nice one on the 30th of April. It was, unfortunately, it was so windy I couldn't shoot video, so I was reduced to taking snapshots and picking the one best snapshot and going with that. Blair McDonald, M101, popular target, it seems, in April. And Blair's shot of the Virgo galaxy cluster. So you can see Markarian's chain on the bottom and a bunch of other galaxies everywhere. How many were in there, Blair? Did you count them?
There's an annotated image on my
yeah,
but let's just say lots.
Lots, yeah. Yeah, right there. Yeah, yeah, nice shot. Bob Russell took this shot of the moon and Venus, 25th of April. I'm not sure. Yeah, it was the wrong place, I think.
Well, when
There's something bright though.
Lisa's picture,
Yeah.
the orientation of the moon's on the other side, but
yeah.
the position of Venus looks like it might be the same.
Yeah, it might be. Might be.
Because over a 2-week period, it's going to shift up.
Yeah. Yeah, we'd have to.
5 o'clock to the minute. Yeah, that's.
Yeah.
I think that'd be Saturday.
Yeah. Anyone got Stellarium on their phone? Have a look.
Ecliptic is usually
No.
about a finger's width below the path of the moon when it's at quarter.
Yeah.
So that would be in a line. Saturn Venus would be.
You couldn't see it though when you took the picture. Yeah. Okay. All right. Well, a mystery. Darren Talbot, He took these shots with his C-star S50 of the Orion Nebula and the Rosette Nebula. And Gary Weber, Venus and the Crescent Moon, with a few stars and moonlight on the clouds. Nice shot. And that's it for April. All right. So Blair is the next person up. Our guest speaker, Blair McDonald, well-known Halifax Center astroimager.
Special presentations.
Yeah.
It works. Okay, good. Okay, everyone hear me okay? I don't know. Hopefully Zoom can hear me. I can talk loud for everyone here, so that's not. So this is a little bit of a refresh of a presentation I did. Oh God, now I feel old. 15 years ago, on black holes back when.
You're breaking up.
I did it a second time then. Yes, you're right. Yeah. So at any rate, this is my presentation of black holes. It says a layman's view, so treat it as that. What's that? No promise. Okay, do I point, Jerry?
Anywhere. That's because something I did. No.
Oop. There we go. So let's take a look at what black holes, first off, what they aren't. So given our conversation a little while ago, Paul, black holes are not vacuum cleaners of the universe. They're, okay, try it again. There we are. They do not suck matter in for light years around. As a matter of fact, black hole has no more gravity at some distance away than a star that formed. So if Earth were in orbit around our sun and our sun mysteriously became a black hole instantly, aside from the fact that it would get very cold and very dark, we wouldn't know it. The Earth would continue in orbit just like it always does. The fact that it becomes a black hole does not mean that its gravitational pull at a distance increases. What it means is you get much closer to it. That's where the problem comes in. What we believe stellar black holes are. So they're cut-off regions of space-time caused by extremely high matter densities. And we're going to take a look at just how high some of the densities get in stages before you form a black hole. We don't really know what the density is inside a black hole. The theory goes to infinity. So your guess is as good as anyone else's. We believe black holes formed by stellar collapse. So if you can picture, you have a star much, much bigger than the sun. It eventually crunches down into something, and the something could be a black hole depending upon the mass of the star. So because black holes are intimately related to the life cycle of stars, let's take a quick look at how stars are born. Most stars form the same way. They form out of huge clouds of gas and dust called nebulae. And examples here, shots that I've taken both from, okay, that should be the laser pointer, both from my driveway in Bedford and from St. Croix. The Horsehead Nebula, and you can see all the gas surrounding those stars. The Orion Nebula, again, about the size of the full moon in our sky, and it's just loaded with gas and dust. And gravity causes that gas and dust to begin to contract. And as it contracts, the core gets hotter due to increases in pressure. And when it gets hot enough and the core gets compressed enough, fusion starts. And that fusion marks the birth of a star. So we've got this core of material that has been swishing down under gravity. And eventually it gets hot enough and the pressure gets high enough, fusion kicks off. Okay, now let's quickly how stars form. How stars die depends on their mass. So small stars go with a bit of a whimper and form white dwarfs. Sun falls in that category. So Sirius B, the other 7 dwarfs. Larger stars go out with a bang. They tend to go into supernova explosions, and they form either neutron stars or black holes if what's left over is big enough. So let's take a look at the first choice there in the death of a star, a white dwarf. So if the stellar remnant, I'll back up just a little bit here. If you can picture a star dying, the core has been burnt in fusion, has been burnt in hydrogen in nuclear fusion for most of the star's life. Eventually, however, it runs out of hydrogen at its core, and the core starts to collapse because now there's no outward force to overcome gravity. However, once it collapses enough, the pressure and temperature get high enough that it can now start to fuse helium. And the star then puffs upward because now fusion is supplying energy to overcome gravity and the star expands again. This goes on several times as the star burns heavier and heavier elements. Each time it does, the star puffs out and then the core collapses once it runs out of helium. Then it puffs out again and it's burning carbon, if I remember correctly, Dave. And you can see that in some of the stellar remnants that are out there. So here we have planetary nebula called M57. This is the Ring Nebula. And the shot most people usually see is just this inner area here. And that little dot right there is the white dwarf that's powering this whole thing. However, you can see the results of previous episodes of expansion and contraction in the star as it puffed off its outer atmosphere. So you can see several shells. There's an outer shell here. There's that shell, and then there's what most people normally think of as the Ring Nebula. So there's been several episodes of the star shrinking down, expanding, shrinking down. Each time it does, it puffs off some of its outer atmosphere. So if, however, after it's done that, this little star in the middle here, if it has less than about 1.4 solar masses, so 1.4 times the mass of the sun, what's left over can be saved from complete collapse. Okay, now it's gone again, Jerry. Okay. Electron degeneracy pressure can provide an outward push that can counteract gravity. Now, electron degeneracy pressure, although very hard for me to wrap my tongue around, basically what it is as this material collapses, we're going to consider it to be sort of a constrained system. It's like all the materials in a bottle. In this case, the bottle is formed by the gravity holding the star together. As you try and push material in there, the electrons in this cloud of material take up all the available energy states. Once all the states are taken up, the electrons begin to push back as you try and push anything else into that system. That pressure is actually fairly strong, and if the star is less than about 1.4 solar masses, it's strong enough to counteract the gravitational field, and the star will balance and sit there for eternity, effectively, forming a white dwarf star. Okay, it won't forward, Jerry, so I'll get you to hit again. There we go. These remnants have, me, is what is an insane density. Think about it. This is the mass of the McDonald Bridge in a teaspoon. Put it to you quite bluntly. There's hundreds of tons cubic centimeter. Those stars are simply outrageously dense. And the radii of these stars are a few thousand kilometers. So I'll give you an idea, last numbers I read, if the sun were to form a white dwarf, which it will eventually, might end up being 3,000 kilometers across. So something with most of the mass of the sun shrunk down to 3 kilometers. So that'll give you an idea of just how dense a white dwarf is. Now, here is a picture of Sirius and a white dwarf. It's kind of hard to see. Actually, it shows up here better than it did on my computer screen. A lot of people think this is the white dwarf. It's not. The companion of Sirius is this little dot way in here, in the glare of the star. And I know, Dave, you've seen that through your telescope with an appropriate mask. Octagon?
Funny pass you can make, which makes Sirius look weird. But it has oriented, right? Seems very close to them.
If I remember correctly, it throws the energy of this halo around the star into those diffraction spikes, and then you can make the star right. Oops, sorry. You can make the star right here out in a gap between the diffraction spikes. So it's something you can view visually. It is exceedingly difficult to get a picture of. Now, I took this picture with my Canon DSLR quite a few years ago now, and give you an idea, the brightness ranges between Sirius here and the white dwarf right there is more than the dynamic range of the camera. The only way I was able to get this was that's like 3 hours, 2 hours or 3 hours of 1/10 of a second shots, thing like that, all added together to get sufficient bit depth to be able to see that. It's a really difficult thing to shoot with a DSLR. A little bit easier with a 16-bit CCD camera or a seamless camera that I've got now, and I'm thinking of redoing this shot to see if I can ping it out any better. So next step along the way is a neutron star. So if the star is a little more massive than 1.4 solar masses, electron degeneracy pressure cannot overcome gravitation. The star will then continue to collapse. There's still one more thing that can save this star, though, and that is if it is below about 2 solar masses, we can save the star with neutron degeneracy pressure. Same thing as electron degeneracy, I can't say that, degeneracy pressure, but it's now from neutrons, and it's substantially more forceful than what an electron can generate. Again, the neutrons take up all the available energy levels, and you try and push more in, and they push back. And typically, these neutron stars are created in a supernova explosion. So this particular one here is M1. It's a supernova remnant known as the Crab Nebula. It does not look like a crab in long exposure pictures. It looks more like brain, complete with brainstem. But when you look at it visually in a big enough telescope, you don't see all of this detail. You see these lines here, and they sort of look like crab claws go to the thing, which is where the name came from. So if you can picture what happens here now, the material that would normally stop at the white dwarf stage can't, because the star is too massive. It continues to collapse, the pressure builds, and eventually it hits the point where neutron degeneracy pressure stops the collapse. So this material, though, is now crashing in at high speed. It hits this core that bounces. That bounce is what makes a supernova explosion. The outer layers of the star blow off into space. The resulting densities of a neutron star are in the order of millions of tons per cubic centimeter. Start thinking the mass of Mount Everest in a teaspoon. That'll give you some idea of just how dense these things are and how incredibly massive they are. We're talking the mass of a sun that is over two solar masses, so over twice the mass of our sun, rather, in a radii of only tens of kilometers. So just incredible densities. And here's some evidence of a supernova explosion. This was an image I took many, many years ago from my back deck of M81. And the only reason I included it is after I took this, probably about 6 months after it, not quite, close to 6 months though, a supernova went off in this galaxy. And here's the supernova right here. So where that arrow is, you notice there's nothing in that original image. Here's the supernova explosion in that galaxy. Now, I have been waiting a long time to say this in a presentation. In a galaxy long, long ago and far, far away, we had the supernova explosion. And if you take a look, every star in this image, with the exception of the supernova, are stars in our galaxy. So M81 is something like 42 to 47 million light years away, if I remember my numbers right. This is a star tens of millions of light years away in another galaxy, and it is outshining many of the stars in our own galaxy. That's how bright those explosions are. So we've looked now at two possible ways that stars can die: white dwarfs and neutron stars. What happens when what's left over after the supernova explosion is still more massive again? And as that star shuts down, the end of its life, gravity overwhelms all known forces. There is no known force that can prevent that collapse. That's not to say there isn't one, just we don't know of. The star collapses in on itself, and if the mass of the core is over 2 solar masses, it's just going to keep collapsing as far as we know. This is kind of an interesting diagram that, if I remember correctly, I borrowed from Stephen Hawking's book, A Brief History of Time. What it shows is the mass of stars here in solar masses. So this is the mass of the sun, 2 times the mass of the sun, 3 times, and so on. Here it shows the radii, or the circumference, I should say, of the particular object you're looking at. So planets, which have a density typically 10 to the 5th gram per cubic centimeter down in this area, just sort of sit there. They don't do anything in particular, so other than go around the sun. So when the sun dies, however, it will shrink in diameter with still maintaining most of its mass, and you come to this line in this plot. Now, what this line is an indication of where the star will end up. What I mean by that is, as the sun dies, it will become a white dwarf. And white dwarfs exist along this portion of this graph. If they are less massive than the value down here, typically that's for planets fly, not stars. If they are more massive than about 10 to the 9th grams per cubic centimeter, sorry, densities rather are higher than 10 to the 9th grams per cubic centimeter, that mass is unstable and that you can't count on them remaining as a white dwarf. They could continue to collapse and become neutron stars. However, once you get to the mass of Procyon, okay, you can see it will definitely collapse to this portion of the graph, which is where all the neutron stars lie. And you can look at the circumference of the star in kilometers and the mass of that star. And take a look, we're talking something 100 kilometers across with a mass of Procyon, so we're looking at just under 2 times the mass of the sun. Think how dense that object is. Right? You're talking something 2 times the mass of the sun and a little less than 100 kilometers across. If the star has more mass, like Sirius coming in a little over 2 times the mass of the sun, at that point, it cannot become a neutron star. Now that assumes that what's left after the supernova explosion is still more than 2 times the mass of the sun. It will form a black hole. So I kind of like this plot, and there's another one that I saw once upon a time and haven't been able to find again. And what it does is, rather than show it as, oops, there we go, rather than show it as mass and circumference, plots what type of star you will end up with against density, which is kind of an interesting plot. It becomes more of a straight line, which is kind of interesting. Just as a historical perspective on black holes, they were really sort of, I'm not going to say predicted by relativity. They fell out of the research that other people were doing on relativity. And Einstein, of course, developed the general theory of relativity around 1915. Schwarzschild showed that any sufficiently large mass will form a cut-off region of space-time. It will have an event horizon. And the diameter of that event horizon is given by this nifty little formula here. Told you there would be math. It's actually a reasonably easy formula. It's just 2 times the gravitational constant times the mass divided by the speed of light squared. It'll give you the radius of the event horizon for that star. Tony, you got a look on your face. It is a big number, yes. Chandrasekhar showed that massive stars must collapse to a singularity. Singularity is what we think is predicted to be in the middle of a black hole. Now, what it is it's a spot of infinite density, 0 size, and the mass of a star. And Wheeler came up with the term black hole rather derogatively because he didn't like, as physicists of his time also did not like, the concept of infinite density. We still don't like it. We're still looking for something to prevent singularity. You don't need to have a singularity to have a black hole. All you have to do is have enough mass to form an event horizon. Now you get a black hole. What's inside it? Anybody's guess. All our theories break down at the moment. We're still looking. Finally, the outcomes were accepted and started to be studied by other people. People like Thorne, Hoskin, and several others. So, a little general relativity primer. This is what general relativity is. Very nice, easy to understand, simple equation. We won't get into the fact that these are not simple terms, they're multi-dimensional tensors. So I'm an engineer by trade. My math isn't going to cover that, I'm sorry. However, if you expand all the terms in that equation, and it was a comment from my wife, add in the incomprehensibility factors, and solve for a term not even in the original equation, you get what everybody thinks relativity looks like. It doesn't look like that. It is actually, a relatively simple equation. It's relatively, in its initial thought, relatively simple theory. However, when you dig into the details, things get very complex very quickly. So, as I said, developed by Einstein in 1915, and he developed it to pick up where special relativity left off. Special relativity deals with, I can never pronounce it, Galilean reference frames. Oh, physicists love to talk about reference frames. And a reference frame is how you measure things, what you measure them against. So I'm standing here in a room, you're all seated in this room, and in my reference frame, you're all still, except for Dave, who's squirming over in his chair. But in reality, we're standing, or I'm standing on the Earth, spinning around at about 700 kilometers per hour on a planet that's whizzing around the sun, 2,000 kilometers an hour, around a sun that's whizzing through the galaxy at tens of thousands of kilometers an hour, and our galaxy is whizzing through the universe at kilometers per second. So, if I'm going to say that Jerry, sitting in front of me here, is still, I have to say what frame of reference I'm measuring that in. So, a Galilean reference frame is a frame where two things have constant velocity relative to one another. Whether the velocity is zero, close to the speed of light, it cannot be changing. And that is the limitation of special relativity. It was developed for a Galilean reference frame. So, what general relativity does, extends relativity, accelerated reference frames. And in doing so, it equates gravity with warp space. It also equates it with the force of acceleration. And I don't know if any of you in the room have ever talked with Roy Bishop, but Roy will slap your fingers if you say the force of gravity. It doesn't exist, right? That's what relativity did for us. It gave us an explanation of gravity, and the explanation is not one of a force acting on an object. What relativity does is it allows us, for the first time, to realize that space is not static. It's not a stage where everything takes place. If you've got a large mass in space, it warps space. That warped space tells that mass how to move because the mass is moving in a straight line. Now you warp the space, and it looks like that mass is moving in a curved line. As far as that mass is concerned, it's still moving in a straight line through warp space. That, it turns out, is what gravity is. And there's a real neat thought experiment that demonstrates two things. It demonstrates how the force of gravity can be related to acceleration, and it also demonstrates the concept of a reference frame. And the picture I'm going to use here is again stolen from Stephen Hawking's A Brief History of Time. And I like the picture because of how it picks a reference frame, a window frame. So we have our reference frame, which is the window. There's a guy holding the reference frame still. And there's, here we go. There's a can right here. So we're going to go over here. The cannon shoots a cannonball up. And at the same instant that the cannonball is fired, the poor sot holding this reference frame jumps off a cliff. So to someone standing on the ground, that cannonball, if I can get my pointer back, starts to follow a curved trajectory, and you can see it here. It's very familiar to anyone. You throw something up in the sky, it sort of arcs over, and it comes back down to the ground. But if you are now in the reference frame of this person falling off the cliff, looking through the window, and you are measuring where the cannonball is at every instant in time, relative to the falling window, all of a sudden, it's following a straight line. It's not following a curved arc. See, the line just goes straight up until it hits the ground. That gives you an idea of how, when I accelerate downward, the effects of gravity can disappear, because now there's nothing pulling that ball down. It's going in a straight line, as far as the guy falling is concerned. You may dispute that gravity disappeared when he hits the ground at the bottom, but at least while he's falling, there's no gravity. You can run that same experiment backward. And what I mean by that is, if you were to do this experiment out in outer space where there's reduced gravity, again, Roy would shoot me if I said there's no gravity. And instead of jumping off a cliff, I have this reference frame attached to a rocket ship. And the rocket ship is going to fly in a direction which, pardon the expression, from the point of view, it's going to fly in an upward direction, right? Now what's going to happen is the ball, which in space is traveling in a straight line, is going to look like it follows a curved path, just like it would on the ground. You can see from that that acceleration and gravity they behave the same. General relativity takes that a step further and says not only do they behave the same, they are the same. Now, keeping that in mind, black holes are one of the simplest and at the same time strangest things in the universe. The reason I say they're simple is they only consist of two things. A spherical event horizon, so the star that produced the black hole was not spinning. And we're talking a mathematical fictitious black hole here. And a completely cut off area of space-time known as a singularity. Now what I mean by that is gravity, that non-existent force, has warped space so much that space has warped back in on itself. You can't get from inside to outside anymore because there is no path. If you continue traveling that way, you will get back to where you were, behind you. Space has completely warped around itself. And at the same time, black holes are quite simple. Black holes can be fully described three things. They have a mass, they may have charge if there was an electric charge in the material that formed them, and they can have spin. They can't have anything else. Everything else that could possibly have information in it, was the matter red? Was it giving off light? It's all gone. It's all radiated away when a black hole forms. Non-spherical, non-spinning masses collapse to spherical black holes. Doesn't matter if that mass starts off square or if it started off a long line, it will form a spherical black hole. Again, assuming it's non-spinning. All traces of any magnetic field or anything else other than mass, charge, and spin from the original star lost, as far as an outside observer is concerned. We don't have a clue what's inside. And just to give you an idea, here's a star. For whatever reason, this star has a little bump on the side. And as it collapses, you can see the bump is still there, but that bump radiates away as gravitational waves. And what's left, no matter what shape this star had, is a spherical black hole. So it doesn't matter how complex the star was, when it forms a black hole, it forms a very simple thing, a spherical black hole. Again, assuming it's not spinning. Now, do black holes last forever? They don't. They radiate away very, 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 very. Anyone more very in there? Slowly. And the way we think that happens was discovered or developed by Stephen Hawking. What happens is a virtual particle pair pops into existence near the event horizon of a black hole. If you've read anything about quantum mechanics, you'll know that space is not empty. And when you get down to the smallest scales, particles are literally popping into existence and popping out of existence. When they pop into existence, they pop in as a virtual particle pair. You have two particles. It's not quite an exact comparison. You can think of them as a particle and an antiparticle as an example, right? And they borrow energy from the vacuum, space-time itself, to form. Well, unfortunately, there's a lot of interest with this borrowing, and they have to give that energy back. They do so almost instantaneously. They combine and annihilate one another, except when they form near the event horizon of a black hole. Now it is possible that one particle can fall past the event horizon into the black hole. When it does that, it combines with the mass of the black hole, but it has negative energy, so it slightly reduces the mass of the black hole. And the other particle now has sufficient energy to become a real particle and fly out into space. We see that particle as radiation coming from the black hole. So it's actually not coming out of the black hole, it's coming from the region around the event horizon. As far as we know, nothing can come out of a black hole. But the net effect is the same. Because one particle falls into the black hole, it will slightly reduce the black hole's mass. Over billions and billions, and I say it like Carl Sagan, over billions and billions of years, these particles falling into the black hole will reduce its mass further and further and further, and eventually it will disappear. We may actually be able to see that happen on an astronomical scale, not too distant future, because we believe there were what's called primordial black holes formed when the Big Bang happened. And they're tiny, tiny, tiny little black holes. And they should have just about finished radiating away sometime soon, within the next billion years. And what's going to happen is when they finally get to the point where they can no longer claim to be massive enough to have, or the density is not high enough, to have a black hole, they'll go, oof, release energy. We might be able to detect that. People are actually working on methods now to detect that happening. That's pretty much what the rest of this slide sums up. So there are some really weird relativity effects that happen around black holes. Even though they're really simple, they are some of the strangest things out there. And you do not need science fiction to have strange things happen. You just need a black hole. So the extreme warping of space-time near a black hole causes time to slow down. Remember, the more massive an object, time gets slower. Sorry, the closer you get to a more massive object, I should say, your time slows down relative to someone far away. So as you get close to the event horizon, time slows down more, and it actually stops at the event horizon. So you think about that, someone falling into a black hole, as far as they're concerned, they'll cross the event horizon, fall through, and eventually get shredded by the gravitational tidal forces. However, to the outside world, time stops when they hit the event horizon. So how do they pass through? Someone in the outside world, they will take forever to fall through. So I'm seen as this poor unfortunate soul, well-known physics term meaning grad student, As far as he's concerned, falling in, time continues at a normal rate. He just fell through, disappeared into the black hole. However, as they fall through, they get torn apart by the tidal forces from the singularity. Because of this extreme warping of space, they look up as just about to fall through the event horizon. All light comes from a narrow spot above them. To see behind them, they look in front of them, because space has warped almost completely around. And again, from Stephen Hawking's book, this is a reasonable diagram showing it. You're near the event horizon, and all the light rays are following this bent space. They're traveling a straight line through warp space. And space is so extremely warped that this particular light ray, and unfortunately the diagram doesn't carry it far enough, actually comes from behind the star. So all light, you only see light looking straight up, away from the black hole. And it's a 360-degree field, including look from behind the black hole, seen by looking up in front of the black hole, if there's such a word. And a black hole, as we said, warps space around it. If it's rotating, it will drag space-time around with it. So as it's spinning, it will drag space-time. It turns out you can actually, in theory, use that as an energy source. You could power an entire planet just from a spinning black hole. And it's possible to get closer to a large black hole than a small one. So people think of, you're flying through space and you're really unfortunate that you fly into a stellar mass black hole. Well, of course you would be, but the thing is, you would start to notice effects as you got closer, hopefully in time to avoid going through. If it's a supermassive black hole at the middle of a galaxy, you're much further away from the center of that black hole when you hit the event horizon. And the tidal forces are much less. You could actually travel through it and never know you traveled through it. You'd find it pretty quickly afterward, but you wouldn't know that you had gone through the black hole because the tidal forces are quite low. It can even be a fountain of youth or time travel. So you're thinking you're flying a rocket ship and you're dangling from a rope, pretty good strong rope, near the event horizon of a black hole. So time is seen by an observer far away. For you, slows down. So if you had a radio system that was, putting out a pulse every second, time interval between those pulses for someone far away looking at them would get longer and longer and longer. The trip would only take seconds in your time frame. You just swung down and came back out, but it could take decades in the time frame of that outside observer. What that means when you think about it is if you fly in close to a black hole and back out, you didn't come back out at the same time you went in, because for you, time slowed down. You're still in your, if you're fortunate enough, early 20s. That guy outside watching is now in his 80s. You've traveled through time, forward, unfortunately, not backward. But black holes allow that. And we believe black holes are the power sources for quasars. When you get millions of solar mass black holes that reside inside some galaxies, and we will get into pictures of that in a bit, as the matter spirals into these black holes, it heats up to incredible temperatures, billions of degrees. The radiation given off by this extremely hot material spiraling into the black hole is a source that can power the quasar. We believe that these rotating regions must be smaller than a few light days across because many quasars vary their output on a timescale of days. If you think about it, if it were light years across, nothing can travel from this side of it to this side of it in under a year. So you wouldn't expect to see variations in output on a daily basis. Right? So what we get is We now, by measuring how fast the material is spiraling around, calculate that there are millions, where'd it go? Millions of solar masses in that central area, but we know it can't be more than a few light days across. And calculate the density required for that, and it's denser than a neutron star. That's why one of the reasons we think quasars are powered by black holes. Now, do we have any proof of black holes? And the short answer is, up until very recently, not a lot. It was mostly circumstantial. We could measure stars that were moving in orbit around something. That's how we found Cygnus X1. It's an X-ray source. All right. So we looked, we figured, okay, there's an unseen companion causing this star, Cygnus X1, to go around in orbit very quickly. We can calculate its mass. We know it had to be smaller than the orbit of the main star, and we think it's a black hole. We can see decaying pulse trains as matter falls in. Several have been detected. What happens is, as matter goes in, as it crosses the event horizon, it gives off a puff of energy. We can measure that, and we've seen these pulse trains decaying as they go down. The reason they decay is the closer they get to the event horizon, time slows down, so we see the pulses get further and further and further apart. But basically, nothing else could cause these other than a black hole. And this got termed the Venus approach. And that comes from a quote from someone once upon a time in the mid-70s, a physicist. And the only reference I've seen is it was attributed to an unknown physicist at a convention. But basically it's this. What do you see when you look at Venus? You see clouds. That's all. So basically you didn't see anything. Well, what was on Earth when there's lots of clouds? Lots of rain, rainforests. So it went a little further. If you had rainforests, and it was long ago on Earth, well, you had dinosaurs. So the conclusion from not seeing anything on the surface of Venus was there were dinosaurs on it. That became known as the Venus approach. Right? We can't see anything about black holes. So we came up with all sorts of weird ideas of what might be there. So this is a sort of schematic of Cygnus X1. We have the large visible supergiant companion star. We have a black hole that's in orbit around the star, and it's close enough to the star that it is hauling off streams of material that then spiral into the black hole. As they spiral into the black hole, typical of things that are spiraling in and spinning, they form a polar jet. So, I'm going to use north and south. God knows whether it's north, south, up, down, whatever. To the north and south, we get the jets material that are streaming away from the black hole. Now, the interesting part about that is here is the field. And can I see it on here? Yep. Okay. Here's the field around Cygnus X1. It's the Tulip Nebula. But if you look over here, by the way, if anyone's curious, that star right there is Cygnus X1. If you look over here, can you notice that feature right there? It's a bow shock from one of those jets. So you've got a jet of material coming off the black hole that's in orbit around that star, shooting this way. It eventually hits the interstellar medium, and you get this bow shock right here. There's some evidence of a black hole. That happens to be a shot I took at our cottage a couple of years ago with just an amateur telescope. So you can yourself get some data that's indicative of things like a black hole. Now, things have changed recently. When I say recently, I'm talking in the last 20 years. They really changed in the last 5 years. Hubble and Chandra, two space telescopes, they're able to view and take spectra of accretion disks around these black holes. Now, when I say these black holes, I'm talking about the giant black holes at the middle of galaxies. Hubble has imaged the cores of several galaxies and found disks of spinning material. And we can measure the rotation speed of that material by its Doppler shift. So we're looking at it in radio telescopes and visible or optical telescopes, and we can measure blue shifts and red shifts of this material. As you can picture, when the material is coming towards you from one side, the assumption here, by the way, is that the plane of the rotation is this way, sort of perpendicular to your plane. So when the material is coming towards you on one side, it's blue shifted. On the other side, when it's going this way, it's red shifted. We can measure that nowadays. And here's ground-based image of a galaxy. It has to be NGC 7052. Here's Hubble's image of the field in the square. You can see there's a huge disk of material spiraling around something that's bright at the core. And when we measure the spectra of things like that in other galaxies, one happens to be the core of M84, we get a classic Doppler shift. When the material is moving toward us, it's blue shifted. It's moving away from us, it's red shifted. Knowing how much that shift is, we can calculate how fast that material is going. Knowing roughly how far away the galaxy is, we can get some idea of how big that spectra is coming from that green sort of slot there. We can get some idea of how big that is. Knowing how big it is and how fast it's moving, we can calculate the mass of what's at the center. And it turns out it's black hole masses. It's millions of solar masses. So some of the things that black holes can do in the middle of galaxies is they can produce rather interesting looking jets of material. This is a shot taken from my, as I said, humble telescope in my driveway. And here is the jet at the core of M87. This is a jet of material coming out from this huge supermassive black hole at the middle of that galaxy. Oops. Right? This particular black hole we calculate at having over 2 billion solar masses, 2 billion times the mass of the sun in a little tiny space. And that jet is over 5,000 light years long. So think about that. That jet is moving fast enough that it maintains its collimation as a thin jet for 5,000 light years before it slows down enough in the interstellar medium to start to spread out. It's really being fired out quickly. Here's the Hubble view of that same jet. A little more detailed than my telescope, but you get the idea, right? You've got this, oops. You've got this core here. It's very bright in the image, and it's not that a black hole is bright. The material orbiting around and falling into the black hole is incredibly bright. The black hole itself, of course, is very dark. And it's shooting this material off 5,000 light years long. Just incredible the amount of power that that thing is generating. And finally, just recently, in I think it was 2019, if I remember right, we got a picture of a black hole at the center of a galaxy. Interestingly enough, it wasn't the center of our galaxy, although they were trying for that too, and they finally did get a picture of the black hole at the center of the Milky Way. The problem with the black hole at the center of the Milky Way is we're too close to it. A strange thing to think of, but there's too much material between us and it. So this one, you can see this is, okay, back up a bit. This is material falling into the black hole. The event horizon is here, and this black area in the middle is called the shadow of the black hole. It's called the shadow because it blocks out light from everything behind it. Right? It's actually the event horizon. And this particular picture was taken using the eventual telescope. And in order to get sufficient resolution, you need a telescope that is huge. In this case, about the size of the Earth. And we made that by having multiple radio telescopes scattered across the globe, taking measurement, very carefully timed measurements, and then we build all the measurements up into an image. And this was the image they came up with. This is our first image of a black hole. What's that? You can't, it's black. You're not, the black hole is in here, you're not seeing it, you're seeing the material that's orbiting around it. No, you have to remember that this is where it gets really weird. Space has completely warped in on itself, and you are looking very close to the black hole. And there's another diagram I should have put in here and I didn't. This material right here is not in front of the black hole. It's behind the black hole. But its light is warped around the black hole, and we see it here. So it would not matter what angle you looked at that black hole on, you would see a ring of material around it. Although it's not a sphere around the black hole, and it could very well be orbiting the black hole this way from your field of view, this extreme warping space will always give you this view. So this image was taken, that was right, 2019. So that was our first actual picture of a black hole. And this image has later been improved upon, looked at the polarized radiation from this particular black hole, and they matched it up to the mathematical simulation of a black hole, and it is amazing how close they come. To the point where, did anyone see the movie Interstellar? The black hole in Interstellar, you know, that showed a, it showed a sphere, but it also showed what looked like a ring at 90 degrees to the sphere coming out that way. They actually see that. The image in Interstellar was not just a randomly generated image for a movie. They actually contacted astrophysicists to say, what would it look like? And they gave them a simulation. It turns out that simulation was so accurate that when we finally got a picture in polarized light, it actually looked like the simulation. So we're reasonably certain that what we're seeing here is a black hole. Otherwise, nature is really playing a trick on it. So, any questions that I may or may not be able to answer? Yeah. Yes.
I understand if there's any way other than rotating. It's for the conservation of angular momentum when it has rotation whatsoever before it collapses. And as it collapses,
it's going to be spinning really fast. Yes. Yeah. So the question is basically, when I mentioned earlier, we've got a, you can have a rotating black hole, but a lot of the information I presented says for non-rotating black holes. If I understand your question correctly, you're saying, why would we look at non-rotating black holes when almost all black holes should be rotating? Yeah, the short answer is it may not. The real reason we looked at non-rotating black holes originally, or why physicists did, is the math gets ridiculously complicated once you take rotation into account. So a lot of what you learn about black holes is all related to the simplest view of a black hole, which is when it's not rotating. You notice I said it makes a spherical black hole when it's not rotating, for the same reason that a star is spherical when it's not rotating. But once it starts rotating, it bulges at the equator, right? We think black holes may do something similar, right? But the math for that becomes ridiculously complicated. So physicists trying to understand a black hole try and first understand the simplest version, the non-rotating black hole. Any other questions? Yeah, Jerry.
Why are the jets straight out in that picture? Why isn't it curved like a black hole?
Because they're not coming from the disk rotating around. They're coming off the polar axis of that thing that's rotating. So if you had something that was rotating like this, right, and a jet came off the end, you would sort of see that spiral pattern. That's not what's happening. They're rotating this way, and the jet is coming vertically. Did I see a hand up? A virtual pair, when I say it's the negative component, virtual pairs have negative energy. It's not that one component has a positive energy and the other one has a negative energy. They have both borrowed energy from effectively space-time, from the vacuum. So whatever component falls in has to have negative energy. But the fact that it falls in gives positive energy to its companion. It becomes a real particle, just to make it confusing. That's about the best description I can give you. There, it is a zero-sum thing. Yeah, it is a zero-sum thing, but it's a zero-sum thing with space-time. So you had space-time with no energy, and a particle pair pops in. They have to have negative energy. They had to borrow it from space-time. Now they have to give it back. And they usually do so very, very quickly. But when you're close to a black hole, it doesn't happen that quickly because one falls into the one may fall into the black hole. Not necessary that it will, but it could. Then the other one effectively gained energy from that interaction and can fly away as a real particle. It's not like they are particle and an antiparticle, although that is what we normally think of when that happens. But they both have negative energy to start with. Yep. Yep. Yep.
One is two members of the virtual particle pair to fly away from the black hole. They would have to achieve what they want.
Yes. So you have to remember this is happening outside the event horizon. Oh, sorry. The question was, how can that particle fly away when nothing can escape a black hole? And the thing is, this is not happening inside the black hole. It's happening outside the event horizon, but very near to it. So you think everywhere in space-time, particles are popping into existence, annihilating one another at infinitesimally small timescales. But when you are close to a black hole, there is a discrete possibility that one particle could, the particle pair could literally pop up where one particle is one side of the event horizon, the other particle is the other side. It could pop up with two particles, just above the event horizon. Any sort of combination there, but it has to pop up outside the event horizon. If it pops up inside the event horizon, it's never coming out. Yeah. Any other questions? Yeah.
Presumably at some point will run out of energy.
The question is, when I was talking about white dwarfs, will it shine forever? And unfortunately, fortunately, you are correct, but I didn't say it would shine forever. I said it would last forever. So it will be dark, cold, sitting there forever, right? It won't shine forever. It will shine for tens of thousands of years by its internal heat, basically the heat left over from when it was a star. But eventually it will cool and it will disappear. But it becomes like a planet. It's still there. It just doesn't generate its own, doesn't radiate its own energy. Yeah. Any other questions? Okay. At that, we'll call it a day.
Thanks, Blair. That was very interesting. So we'll have a 15-minute break. Okay, so we're back, and Paul Heath is going to give his reading of Hidden Star. Okay. Hidden Star. There is a hole upon the sky that pulls our wonder near, a maelstrom lost to sight that gathers all with a grip so tight. A blinding flash that pierces time for eons outward racing, even as it steps back from time. Trapped by a hidden might that delays time's passing, its glowing disk outspins the clock, until with sudden darkness is lost to sight. Lost to sight, its hidden strength still holds sway, pulling even passing, rushing light astray, unlocking distant sights from far, far away. In familiar family games, the larger Sib betrays. Upon his spinning maelstrom's glowing disk, he pulls his lesser siblings' flowing tresses, for she cannot dispel his hidden strength, a hidden strength with teasing now displayed. For ages and eons, the hidden strength with growing force gathers all who unknowingly too close do stray. Yet strength even hidden, time's ending cannot delay. Into the distant ages and eons, even the greatest hidden strength, time, will slowly ebb and fade away. I think it was close to Blair's speech. It's Blair's time. The picture was the picture of the Q galaxies black hole was pretty cool.
Thank you, gentlemen. Just a couple of items. It's wanted to note on the scope fund, the St. Croix Observatory Property Endowment Fund. So the Property Endowment Fund. Not that one. So the scope fund is the mechanism by which we're going to fund and maintain our St. Croix Observatory. So we'll be putting some visibility to donations. Donations are open. We have the matching funds. We're close to $2,000 now, I think, in terms of donations received. Just like encourage everyone to think about that in terms of if you're able to participate. This is a wonderful opportunity to double the impact of your donation. Any donations are gratefully accepted. The astro imaging sale, we're going to also do a sale of astro images from center photographers, and that details will be available fairly shortly. We're very close now to having all the mechanics set up to get that running. I just want to also note that we're going to have a donation table that's at Nova East. So anybody, if you've got books or astronomy equipment, there's going to be a flea market and a donation table. More to follow on that, but just wanted to give you an opportunity to think about things that you might have in your possession that you might want to move on. If you're anything like me, you've probably got a fair amount of that kind of stuff, and sometimes it takes a while to figure out what you really want to part with. St. Croix Observing Nights. I did want to note that I'm now the St. Croix Observatory manager. We do running the monthly observing nights. The next observing night is coming up on the 30th of May. I'd like to encourage particularly anybody who's new, any new members of this center, or anybody who's not familiar with St. Croix, to come out. Not only on the monthly observing night, but if you watch the discussion list, you'll see when folks are going to St. Croix. And if there's folks are out there, telescope or not, by all means come out. It's a wonderful opportunity just to see the facility and meet some folks.
I also want to mention that there have been several people ask me, I don't have a telescope, can I go to St. Croix? The short answer is absolutely. There is a 60-inch telescope that members can use up there. There's also an 8-inch telescope that if you want to dabble in is all set up, ready to go. There's instructions on the website, I believe, about, but you do not need a telescope or even a pair of binoculars to go to George St. Croix. The equipment you need is actually. Thank you, Bear. Absolutely. And so it's one of these, if you haven't been, go. And you, as I said, and as Bear points out, you don't need to bring equipment with you, just go. I'm sure you'll enjoy it. You'll learn something about St. Croix. It's not all about observing. It's also about the people you meet and some of the things you will learn as you get out there. So don't hesitate to go. Just watch the discussion list, because it's not always just the monthly observing night. There are impromptu sessions which occur up there. And we're also having our annual St. Croix Observatory Barbecue and Observing session planned for the 19th of September with a rain date. Again, a wonderful opportunity just to see the facility and meet some other members out there. Nova Notes, I want to pass on a big thank you to Lisa and Fanning and to John McPhee for the work they do. We're really fortunate to have this. Is a wonderful, wonderful part of this Halifax Center. A lot of information in there, and so I encourage everyone to have a look at Nova Notes and find out what's going on in the center and what's being planned. I mentioned in this current issue about the observing programs. I want to put a little plug in for that as well, that the RASC has several observing certificate programs. And if you're interested in doing those, have a look at the link in Nova Notes. There's a link to point you to the site where you can see what these observing programs are. And again, come out to St. Croix if you like, and talk to some folks out there. There'll always be someone there who knows something about some of these programs who can probably help you out a little bit. And finally, there is when you run a center like the RASC Halifax, it's a volunteer operation and people change on the board of directors. We're very fortunate to have policies and things which help us keep ourselves centered and keep documentation correct. And there is a new policy regarding document retention, which you can see on the website, and there are some position descriptions available in there. But again, encourage folks just to have a look around at our website. You can see lots of interesting information in there. Anything further, Judy, you want to add on that? Okay.
Please inform us.
Okay, Peter. So Peter Hurley is Peter is the co-chair of the Dark Sky program, so that's an update for you.
Okay, so I have to talk about a couple of events that I'm involved in. As Tony said, I'm co-chair of the Dark Sky Preserve Committee for the Center. Andy Schelling is the other chair, and one of our responsibilities is to coordinate the Dark Sky Weekend 25. This is the 16th annual Captain Kuja Dark Sky Weekend. It's a public event open to anybody that's staying in the park over the weekend. We're looking for volunteers. Last year we had 14 volunteers. The park provides us with 6 campsites. Some of those are powered. But because we have enough volunteers, we ask everybody to share campsites. So we typically end up with 2 or 3 tents on a campsite, so we can't accommodate trailers or RVs. If you want to volunteer and you have a trailer or an RV, you'll have to arrange your own campsite. But apparently campsites are a commodity on the internet now. I think the park is booked for the weekend at this point, but there's a couple of Facebook pages, I think, where campsites get traded and that sort of thing. Dates are August 15th, Friday, until Sunday, August 17th. And for those that haven't been involved before, I'll just run through what the program's going to look like for the weekend. It's very similar to last year. Friday evening, starting at dusk in the Scott Circle, there'll be an introduction to the RASC Dark Sky program, Dark Sky Preserve program, and discussion about the park designation as dark sky preserve. That happened in 1990, I think. David Chapman and Quinn Smith were the people involved in doing that. I'm sure there were others, but were the principals. We'll also talk about Dark Sky Weekend and our partnership with the RASC Halifax Center partnership with the park. We'll also talk about the use of laser pointers, because we will be using green laser pointers during the sky tour, and I'll get into laser pointers in a bit. Introduction is followed by a sky tour, and it usually takes about half an hour. When it's finished, there'll be observing in the field. Members set their telescopes before dark in the field, and then the public are invited to come and speak to observers, look in the eyepieces, ask questions. There's also a binocular table set up, and people will be taken through the use of binoculars and given a sky tour with binoculars. Yeah. Saturday afternoon, Merrimack Edge Beach, we have an astronomy info table. We stand and, well, there are actually people that come to the beach just to talk to us, but usually we're trying to stop people that are on their way to the beach or on their way back and talk to them about astronomy and ask any or answer any questions that they have. We'll have telescopes on display, always attracts some attention, talk to people about how telescope work, that sort of thing. We occasionally have someone that will bring a telescope to the park because it's dark sky weekend. Last year, somebody came along and said, have this exact telescope, and I can't make it work. So we brought it to the dark sky circle at night and set it up, and somebody can get it working. Solar observing, if weather cooperates, we'll have called a solar telescope set up. I say workshops with a question mark. Certainly Tony Schelling in the last couple of years has tried to do something with sketching, and I try and do something a little bit more formal with workshops this year and advertise it ahead of time. There'll be 30-minute or 1 hour time slots. One might be on sketching, one on the use of binoculars. Some ideas, we'll see where that goes. Also Saturday afternoon at the Sky Circle, we'll do something called Rock the Solar System. That's usually popular. Where we set out a scale model and paint out the distance between planets. So it's a lot of fun. Daytime observing, talked about this. We haven't done it yet. I don't know whether we'll do it this year. There are 4 planets up, I think, at that time. But it'll be a bit of a challenge, so we'll see whether we go ahead with it or not. The evening program, Saturday program is going to be pretty much the same as the Friday evening program. Last year, the park presented a premiere of Moon and the Seven Bird Hunters story. It's an interactive program. Kids are involved, and it's a great story. It's presented in English, French, and Mi'kmaq at the same time. It was a thrill to see last year, and we're hoping that they'll do it at least one of the nuts that were there for our Sky Weekend. Sunday afternoon and Sunday evening programs, they're pretty much the same as the previous one, if weather cooperates. Certainly we got a little creative last year because it clouded over on Sunday. We didn't get rain, so we didn't cancel. But anybody had imaged and had a way of displaying their images on a laptop or a tablet, set up the imaging rig and showed the images on screens, and people went around from different stations. It was better than just sending people back to the campsites. So we'll see what we can do. The thing I wanted to talk about just briefly is laser pointer training. Anybody that's used a green laser pointer for astronomy outreach, or they've been involved in a sky tour where a green laser pointer was used, they know how valuable a tool a green laser pointer is. Unfortunately, there are people out there, I don't understand why, but they get kicks out of shining these green laser pointers at aircraft, particularly when they're on approach to landing. So in June 2008, the use of handheld lasers in Canada became restricted, and it's regulated by Transport Canada. It's illegal to possess a handheld laser over 1 milliwatt in public space inside of the urban metropolitan areas of Toronto, Montreal, and Vancouver, and within a 10-kilometer radius of any airport or heliport. You have to apply to Transport Canada to get a special permit to do that. Outside those areas, you can use a laser pointer between 1 and 5 milliwatts if you have a special permit. It's illegal to have in your possession in a public space or to shine to the sky anything brighter than 5 milliwatts. The RASC Canada, because we use laser pointers in the 5 milliwatt range, applied to Transport Canada, and we've now received a written authorization from Transport Canada to use green laser pointers with conditions. One of those conditions is that you have to be trained and certified in that use. Training's really pretty simple. It's just a matter of explaining to you what the restrictions are, what the conditions are, what the reporting requirements are, just so that you know. And then you can use a green laser pointer in that 1 to 5 milliwatt range. You also have to have a spotter with you watching for aircraft, and that person also has to have the RASC certification. So they also have to be trained. So if you have a green laser pointer and you think you might want to use it for outreach, we can now offer training and certification to members. If you don't think you're going to use a green laser pointer, but you might be involved in an outreach program, everyone that wants to use a green laser pointer has to have a certified spotter. So it's a good thing to just have that so you can be somebody else's spotter. And so the opportunity is coming up at Nova East for us to have a training session. So I encourage you to register for that. Certainly come to Nova East for that. Just a reminder, certificates, or reminder to those have the certificates. Certificates have to be reviewed after 3 years. I received my certificate in 2003, so it expires in March 2026. Has to be recertified. Anybody else that was in that class with me has to be recertified. So Nova East would be a great opportunity and be ready for the 2026 season. Yeah, any questions? The material is online. If I do things one-on-one, it's just a Zoom session. Let's say it's some 30 minutes. In a classroom setting, it might take an hour, but it's not onerous. It's just knowing what the conditions are that we can use these and the reporting that's required as a result. I didn't put those details up there. One of the things that you have to have when you do use a green laser pointer, there are 4 things you have to have on your person. One is your RASC membership. You have to be a member of good standing. You have to have a copy of our written authorization from Transport Canada. And you have to certificate, have a copy of RASC liability insurance on your person. What did I miss? There's a 4th piece of documentation, but I can't remember either. Yeah, you have to have a spotter. You have to notify the center executive before 8 hours before the event. You don't have to receive acknowledgement from the executive, but you do have to send that email to the executive. I think.
In other words, if you're using the pointer,
Oh, yes.
it has to be a recognized RASC event. The way to do that is contract it, say it, let them know what is happening.
Yeah.
Because if you don't do that, you don't know about it, it's not recognized, so you get caught with it.
We have a reporting requirement that individual has to report to the executive, probably Dave Robertson. We're just in the process of putting together a little bit of structure within the center of how we're going to handle all of this, the training and certification. Dave's going to help out with that. Yeah. Okay. If there aren't any more questions, just get in touch with me or Dave Robertson. You can get me at VP at Halifax, RASC.Halifax.ca. Yeah.
Good. Done button. All right. Okay, Nova East. You had a really nice segue for this. It is our theme because at our March, whatever it was, we had a meeting previously with the group as we had a visual astronomy as theme, and so the tagline this year was "Look up." Visual astronomy, and keep in mind, visual astronomy can be naked eye, can be through a pair of binoculars, or can be using a telescope. It's still visual. So it's the weekend of August 22, 25, and lovely enough, new moon dab smack in the middle of that weekend, so we have dark skies, assuming the sky gods agree with us and keep it clear. It is once again at Smiley's, back home, where we belong. And these are some of the presentations that are there. We have, our first talk is on the pros and cons of various telescopes that Dave Hoskin will address. And then Jay Broski and Dave Chapman will address how the eye works and exit pupils. There's a couple of workshops, one on how to make a sundial, and the other one, as Peter pointed out, there will be a training session on the laser training. And I do recommend that anyone that is attending RASC get trained. Even if you don't have a laser pointer, it would be helpful to have you certified so that if somebody is using a laser pointer, you could be that spotter. So it'd be helpful either way. We're in the process of getting a really special speaker, so that's why it's to be announced. I'm just leaving it blank for now. Dave Hoskin will doing the Walk the Solar System. Sherman Williams Walk. It's a memorial walk in honor of Sherman Williams, a former member. And Pat Kelly will be doing birding session for us down at Smiley's. And as Tony pointed out, we are going to have a flea market where you can buy, sell, or barter. So again, spring, do some spring cleaning. Look at that equipment, those books you've got. Think about things you'd like to pass on to someone else that's been gently used. Okay. Something to think about. So don't forget to add that to your calendar. This is a perfect opportunity to socialize with other members and also, if God's willing, to observe. Notice in the upper left-hand corner, there's t-shirts. again, we have our wonderful Lisa Van Fan to thank. She's in the process of designing a T-shirt. Something to do with lookup, so we look forward to another wonderful design this year. And our registration will be officially open June 6th, which is the day before our next meeting, by the way. But anyway, we have observing sessions. We do have the public sky tour both Friday night, Saturday night with Gary Weaver and Chris Young conducting it. We will have a public observing activity, and it's a guided activity for all three types of observing through naked eye, binoculars, and telescopes. We'll have a special list of eyes so that members can, you take your pick. If you want to look at these special things we've noted that you can look at naked eye, you can do so. If you have a pair of binoculars, bring them along. And we have some binocular targets, as well as those that have telescopes. We have some targets for you to look at as well. With respect to the meals, oh yes, there's always public observing in the field, right? But that will be open as well. Meals on Saturday and Sunday, we do have an astronomer breakfast at 10 a.m. as per usual. Keep in mind, we're not offering hot food again this year. It is the muffins, donuts, tea, coffee, juice, fresh fruit type of meal. Friday and Saturday evening, we have an astronomer lounge from 10 p.m. to 1 a.m. And we'll have some light snacks and certainly a kettle available, so if you need to heat up some tea or hot chocolate or coffee, whatever, it's available to you. And then Saturday, around 5 o'clock or so, is the host dinner, which means we are not having a barbecue. You bring your own dinners, but if a group of you know you're going, you want to get the group of you together to collaborate what you're eating, feel free to do so. Won't stop that whatsoever. And it'll all be at the event field if you want to come down and join the group with your dinner. As was mentioned, I think by Tony, there are RASC awards, and these aren't the observing ones, but these are the other awards that are available to us. We had Robin Ford a few months back to explain them all. They are on the website. Go look at the criteria and see if anybody you know in the center fits any one of those criteria and feel that they are deserving of one of those awards. The submission deadline is the end of this year, literally December 31st, and that's where you can find it on our website. With the observing certificates, I think, yes, Tony, you did mention these, but they come out to observe either at SCO or at Nova East. Those are the various observing awards that you can achieve. Explore the Universe is a really nice introductory program. It really is. It gets you familiar with the night sky, the constellations, the movement of the moon in general, planets, some of the dark sky objects as well. So it gives you a really good understanding, so that by the time you go take your telescope, want to get a telescope, you'll know generally where the sky that you want to look at that particular object in. Explore the Moon has two forms. You can do it with binocular or with telescope. The Messier catalog, all 110 are there for you to observe. Finest GCs, I believe, is more of a challenge. I've not really looked more into that one. Isabel Williamson has 135 objectives, is what they're referred to. Features of the moon that you're to look at. Deep Sky Gems, Deep Sky Challenge, and the double stars is actually not that challenging either. It's something you can do from your backyard. You don't need a dark sky to do the double stars. So something to consider. For those of you that are into astroimaging, I know we have a lot of astroimagers in our center, but it'd be really nice if some of you guys would get your act together and actually apply for one of these, because you certainly qualify, right? So think about it. There's the wide field, deep sky, and the solar system one. So think about it, and because I'm actually trying to pitch for anybody to complete those or one of those types of certificates, because our center has not had a certificate awarded since 2022. So it's time to get our acts together, folks. Fingers crossed we can. Meeting dates. Our next board of directors meeting is June 3rd. So if there's anything that you feel should be raised by the board, please let us know before that date, and we'll make sure that it gets addressed. The next members meeting is June 7, which is the day after we open the Nova East registration. our guest speaker is Tony Shelley. Those of you that missed his presentation at Lee's last year, Tony's agreed to present again for us, and it's Women in Astronomy, and it's really intriguing to see the history and the contributions that women through the years have contributed, but have really gone unrecognized. So it's really worth your while to come and see his presentation next month. Our National Council meeting is next day. And then the AGM, you will be hearing something about this in the next few weeks. Jenna, in talking to her, said that she's getting the annual report completed. It's just about done, and then the notice of meeting will go out. It is Sunday, June 22nd, so that's the national AGM. So keep an eye out for that. And I think, yeah. So now I changed my hat from RASC Halifax Center to RASC National Council, which I'm currently the chair for now. So for those of you that are new to the center and new to astronomy, the National Council is the only committee of the RASC that is in the bylaws. It's in Article 8 of bylaw number 1. It's a consultative and advisory body. There are 30 centers represented across Canada. Each center had 1 rep per 200. We have less than 200, so we have 1 rep, and currently, like I said a moment ago, it's me. Some centers, like Toronto Center, for instance, they are allowed up to 4, but they choose to send only 2. So it depends upon the size of your center. The executive are elected annually. They have chair, vice chair, and council recorder. The vice chair is currently Charles Ennis out of Sunshine Coast, and the national recorder is Adriana Stone out of Calgary Center. We have 6 meetings a year, roughly every 2 months, and like our center, we don't meet at all during the summer. The RASC president and the executive director attend every meeting. They are always there, and the president has always encouraged the other board members to attend, and I can only think of 1 meeting where all of them did not attend. And certainly the RASC committee chairs may attend if they choose. The EPO chair currently, Karim Jaffer, and his predecessor, Laurie Roche, have always attended our meeting. Ooh. Working. Oh, there we go. Oops, sorry. Go back up. So the General Assembly, for those that attended it, registered on the April 26th and 27th, you should have received an email on April 30th thanking you for registering, and that the videos are now available to you. Those videos are only available to the members that registered. So unfortunately, for those of you that didn't attend, you won't have access to them for quite a while. And the rationale apparently is that we want to encourage people to attend, but if we only allow a short period of time between G8 when these are available, it would discourage people from attending. It's the rationale I was given anyway. There is a new Observers in Visual Astronomy program out. It was announced, and some of it was previewed at the General Assembly. They were hoping, I think, to have it out in June, but they premiered sessions 3 and 4 and 9 and 10 at the GA, but they had come to realize after doing the beta testing in Vancouver and in Montreal that sessions 1 and 2, as they put it, needed to be lightened up. It was just too heavy in the technology for introducing the programs. They decided that they better make some changes there. So look forward to that. It'll be a really exciting program for training, educating newbies, and maybe even some of the people that are more have been here for a while and really don't know everything. Would be interesting for them to attend as well. As you know, the International Astronomy Day was held May 3rd. We were at the Discovery Center last weekend. Started across Canada. If you want to watch video, and keep in mind it's 4 hours in length if you can skip through to various centers, but it was literally held coast to coast to coast. There were 12 centers involved, from St. John's to Victoria to Yukon. So we literally have it right across the country. There were some really cool things that the centers were doing. So it'd be really worth your while to go and listen to it. I've got some notes to mention to the board, just, Tony, from that particular session. It's really quite cool. Reprinted. Thanks to the RASC PO committee, we have new outreach materials that were reprinted, that hadn't been reprinted in quite a while due to, as you can appreciate, in the last couple of years, there have been some fiscal challenges, but those have been overcome. We do have monies now to reprint these, the Starfinder and the Moon Gazer. We have some in our possession, so if any of you are in an outreach event, you need both of these, please contact our Dave Hoskin, who's our outreach chair, and you can reach him at outreach@halifax.ca. And last but not least, there's a brand new program coming out that was again announced at the GA, and it's a seasonal novice observing program. And basically, it's everything from constellations, asterisms, stars, and storytelling. Depending on where you are in the country, you can choose which indigenous stories to tell. And the program was initiated by I think it was Linda Polita from Sudbury Center, and unfortunately she passed away before it could be completed. So Grim Schaffer, who's the PO chair, what was the person? Joanne Salshi and our very own Tony Schelling took up the torch and developed this program. And it's for anybody, eventually will be for anybody to utilize. And it says seasonal because you've got summer, spring, winter, and fall, all 4 seasons, and got programs lined up for that. So with all this stuff going on, remember to start at feet and look up. Skies are open, right? So that's it. Thank you. Guess I shouldn't walk away with the mic, should I?
Yeah, that's Judy and Peter and Tony for the information. Now, a few things about regarding outreach. I want to thank everyone that came out to Discovery Center last Saturday. We had a very good turnout, both in members that came out to help and the public who got to talk to people about various astronomy-related issues. And the sun came out for a brief time Saturday afternoon, and Peter and Matt were able to go out and some solar observing and rope in people as they came and left the Discovery Center. And they got sunburns. So unexpected given the forecast. We don't have any official outreach events that I know of coming up between now and the next meeting, but there has been interest by members of the public at a couple of other outreach events we've had that they would like other opportunities for a public outreach. So we'll consider that and just keep your eyes open on the announced lists, and I'll let you know if there is one. The boardwalk by the harbor, apparently the city requires permit. Yes, word. Give license. So it's not as straightforward as it used to be, just hauling a telescope down. Having said that, Harry DeWolf Park is a pretty good spot for lunar observing, planetary, and brighter DSOs. The lighting's pretty good there, actually. It's better than the boardwalk. So that might be something to keep in mind.
Side of it, on their
Yes.
own around any airport or airport, so we continue agreement.
Yeah.
What about the about that? Looks like temperature one. Yeah, perfect.
Yeah, it's kind of in the sweet spot. So
That was brought up.
So our this station measure is just outside in 12
good. Okay, so let's end up with what's up in the May sky. We're almost halfway through May. Some of this is past. Okay, sun this month. So short days. By the end of the month, we'll only have 4 hours of true darkness. So if you want to observe anything fainter, you have to stay up late. But there's still lots of the moon and brighter DXOs, star clusters, globular clusters, open clusters that you can observe without waiting for true darkness. The end of dusk at 11:13. You can start at 10. There's some of those. And this is what the sun looks like today. AR 4079 is disappearing. That leaves only 3 smallish sunspots currently, but there is something active on the far side of the sun, so you may see something over the next week. This month, I don't remember what the skies were like on the 3rd. That was a good night to get a nice shot of, or visualize with binoculars even, the moon near Mars and Messier 44 in Cancer. First quarter of the Frog's croaking moon was the 4th, and the Aquariid meteor star peak was on the before dawn on the 6th. Full moon on the 12th is coming up, and on the 13th and 14th, the moon will be near Antares and Messier 4, which is a nice view. 20th is last quarter, 22nd, the moon near Saturn, and after that is Venus. And the new moon, Trees fully leaf moon, will be on May 27th. And following that, once again, the moon will be near Mars. So this is what you would have seen on the 3rd of May if you looked up with your celestial sky master binoculars, one field of view. Would have been nice. On the 13th, at 11 p.m., if you look in Scorpius, you'll see Antares, Antares, the moon, and the cracked globular cluster. Again, a nice site for Celestron 50 by 70 binoculars. And at the end of the month, this will be what you would see with 7 by 50 binoculars, the waning, rather the waxing crescent moon and Mars at 11 o'clock. That's the view of the moon for completing the Explore the Universe challenge or Explore the Moon challenge. Would have been days ago, between May 2nd and sunset. But of course, you can, if you're an early riser, you can get up with the last quarter moon and the similar sorts of things a couple days before and after that. Again, if anyone had clear skies on May the 4th, you could have seen at 9 p.m. the lunar X and the lunar V. And this is it's called a clair obscure effect. And it's due to sunlight on the edges of craters and ridges as the sun's rising over those features on the moon. So for the lunar V, it's caused by the light hitting these ridges above Urquhart, the crater. And for the lunar X, It's the sun hitting the edges of Lacaille, Bianchinas, and Purbeck craters. So you can see the X there. So if you missed it, you'll get another chance in next time around. Well, it depends when it happens. You can see it during the daytime though. So May 20th. This is an interesting one. This is a challenge because you have to be up early. So at 5 a.m. Galactic Daylight Time on the 20th, there's a favorable western libration of the moon, and that will expose Mare Orientale. And this is what you can try to see. So you're going to be looking past the Grimaldi Basin, and there's a couple lakes, Lacus Autumni and Lacus Veris, and then I took this picture, I forget when, but a while ago, and you can just see the edges of the Mare on this one. Planets in May. Mercury is very low in the east and is lost in the solar glare by mid-month. Venus is still prominent, but it's low in the east before sunrise. And the 21st to the 25th of May, Venus will form a line with the waning crescent moon and Saturn. Mars is still in Cancer, visible after sunset. It was near a waxing crescent moon and M44 on May 3rd. On the 25th, it'll cross into Leo. Jupiter is prominent in Taurus after sunset, but it's getting lower and lower in the western sky, and by the end of the month, it'll be pretty hard to see. Saturn's visible low in the east in the morning twilight sky. It had equinox on May 6th. And as I said, it forms a line with a winged crescent moon and Venus on the 21st to 25th. If you do look at Saturn now, you'll note there's no rings. You'll just see a line across the planet because of it tilt relative to us. Uranus is too close to the sun to be visible. Neptune, you can see it in Pisces in the pre-dawn sky. So, for example, if you're up at 4:30 on the 23rd of May and it's clear and you have a good eastern horizon, you get a nice shot here of the Venus, the Moon, and Saturn. Formed not straight line, but in line. Explore the universe. So we're finishing up with the spring constellations: Ursa Minor, Ursa Major, Bootes, Leo, Virgo, Libra. So at these in the late evening, so after sunset, after 10 p.m., good time to look for these. The spring stars: Polaris, Cochat, Dubhe, Merit, Arcturus, Denebula Regulus, Zubin El Nubi, Zubin X Gemini, and Spica. You have to observe these stars and tick them off for the universe. Spring stars. The deep sky object for May is Messier 5. This is a very ancient, dense, populated globular cluster surface. There you got a picture, which I showed you in the montage. So look for Messier 5 below Arcturus in the southeast. And the double star, this is a fairly easy one. Aphera, or Zeta Leonis, and 35 Leonis. So if you look in the Leo, right here, the bend in the neck or the bend in the sickle, that's Aphera. And that name comes from Arabic for braid or curl. It refers to the lion's mane. This is a true double. It's an optical double, because the two stars are quite distant from each other, 174 years. But it's quite an easy double. And if anyone saw any meteors, was it clear on the 6th? No. No. Okay. So could have been good because the timing is good. The moon would have set before dawn, well before dawn, when gradient is high in the sky. And this particular meteor shower is known for persistent trains. And that's it for the May sky. Are there any questions here or in Zoom line? Okay. If no questions, then thanks everyone for attending, and we'll see you a month from now.
Please hang up and try again.